Hi, y'all. Professor Ghassemi here. Welcome back to another lecture on AI agents at Michigan State University. Today's lecture is going to cover two topics, model context protocol and exception handling. As we've done in previous lectures this semester and we'll be doing going forward, I'm providing here some of the key themes that we'll be covering in the lecture today. If you see theme 1, which is implementing agentic design patterns, this means this lecture is going to have some code later in the video. I'm going to show you specifically how we do the implementation on the server and the client side of model context protocol to help build your intuition for how that works. We also will be covering, in the context of discussing model context protocol, some of the mechanisms that are used to assist with the control of AI agents and the governance considerations for AI agents briefly at the end of the lecture as we talk about exception handling. So let's jump straight in to the conversation on the bulk of today's discussion related to model context protocol. So first and foremost, what is Model Context Protocol, or MCP, as I will be referring to it throughout the lecture? The easiest way for you to think about it is as a standardized way for an agent to interact with various external resources. And the hypothesis is that if you have a standardized way for the agent to interact with those resources, you get two real nice benefits. The first is the agents could be particularly prospectively trained on how to do the interactions following the protocol, which should improve their performance. But then furthermore, if you and I both follow the same protocol, I create a standardized way to interact with three tools, and you create the same standardized way to interact with three separate tools, we can combine those. And we can share basically in the tooling that our various agents can use to accomplish tasks. So standards basically help, raise the tide for all ships, or in this case, all agents that will be using the downstream tools. What I have here is one of the workflows that you've probably gotten used to at this point in the semester seeing me introduce when I cover a new topic. Let's step through this, and I'm going to call out basically what makes MCP unique and valuable as we step through it. So here we have a user, that could be you or a user of a tool that you're building. And obviously you're going to provide a prompt with the intention that it will go to your AI agent. Now we've covered in previous lectures this semester that it's super useful for these AI agents to call tools, to call databases as a way to improve the quality of their responses, the fidelity, the trustworthiness, and so on. And what we had covered for most of the semester prior to this point was having this LLM or agent call the tools directly. So if we had a diagram like this, there would have been a line directly between it and the tools, directly between it and the APIs, and so on. But what ends up happening when you have those direct wirings between the agent and the tools or the APIs is that the agent has to learn about the idiosyncrasies of each of those tools, of each of those APIs. And furthermore, if I want to take my code base or my agent, which uses 4 tools, the way I structure the interaction with those tools may be different than if you came up with a way to interact with the same 4 tools. That obviously makes sort of exchanging knowledge between us, if we were going to collaborate, a little more difficult. And this is where the MCP or Model Context Protocol sort of comes into play. The way I really want you to think of it is as kind of like middleware. So it's facilitating the access of this agent here in the pipeline to the tools, but through this middleware called an MCP server. And as we go through the lecture today, particularly when we look at some of the code, I think it'll become very clear exactly what this MPC server is doing. For now, at the level of intuition, all I need you to know is that the MCP server gives this client here, the AI agent, your LLM, a couple of options. It can ask the server, hey, what are the services that you offer? So what sits downstream here? And the server can respond with some of the things it provides. It says, hey, I've got access to these 3 APIs. I've got access to these 2 databases and these 4 tools. And then the second thing that the server allows this AI agent or MCP client to do is ask for one of those tools' outcomes. So he could say, hey, that's great. I understand that you have access to the weather API. Would you mind passing me the output of the weather API for East Lansing, Michigan? I'd like to use that in part of my response. And so these are sort of the 2 major things that the communication between the server and the client enable. One is, what tools do you have available? And the second is, give me the outcome of one of those tools for a given set of inputs. Something that's important to keep in mind right here at the front is that an MCP server, given that it's a middleware, is ultimately a means to some other end. And so if the tooling here on the right-hand side is no good or deficient or tends to return results that are challenging for an agent to use, well, naturally, that's going to propagate back through to the agent at the point of consumption. So Model Context Protocol does not improve or change anything about these tools. Rather, it helps orchestrate and therefore reduce some of the complexity as the agent is requesting information from these tools. Okay. Hopefully this is super clear. If you remember this, everything that follows from here as we dive a little deeper on MCP is going to become clear. So this model context protocol, I motivated it in that previous slide by saying, wouldn't it be great if I came up with 3 tools and you came up with 3 tools, we could share those because we're following the same protocol for how the LLM interacts with the end tools. And what's super exciting is that there are resources that exist on the World Wide Web, such as the one that I'm showing you down here in the hyperlink on the bottom right, that keep a running catalog of MCP server implementations that are publicly available for your use. I'm showing you here literally just a couple of examples. There were hundreds that were listed on the website that I have linked down here, so I think it's worth a read through on your own. But I'll just kind of talk you through the ones that caught my eye, and I'll also speak through the implications of having these available in MCP implementation. So why should you care that these are available? So let's start with this one, arts and culture. So there's an MCP server implementation for a movie database API that enables the AI assistants to search and retrieve movies, TV shows, and person information. So here's what's great about that. Instead of you figuring out how to interact with IMDb's API or Rotten Tomatoes API or whatever other database they're using in the background, writing your own custom parser, your own custom methods in your own custom class, if you follow MCP's protocol, you can have your agent talk through spinning up this server in not too many lines of code. You can spin up this server and the agent can just talk to the server through the protocol to get the information it needs from the movie database API. This is also true, of course, in this other MCP server, but which handles, instead of movies, handles books. Okay. So this is 2 examples from art and culture. What you can see through the diversity of examples I've given here is that these MCP servers have been implemented for all sorts of useful database endpoints, APIs, toolings, and so on. In the sports ecosystem, they have one for Major League Baseball that gives information on players, stats, game information. So you want your AI agent to be able to answer questions from a grounded, authoritative source that may sit in the back of that MCP server. That's a way that you do it. There's also really cool extensions such as tools that enable text-to-speech and vice versa, connectors to databases so that you can describe something in your agent can describe through natural language the right tool within the MCP tool description and then do an interaction with Postgres or some other database that you have as an endpoint. And then we have, obviously some other specific examples that are listed here in the domains of marketing, communication, medicine, and bioinformatics. I decided to show this to you up front before we get too deep into the technical details so that you understand why this stuff even matters. Like, why should you bother knowing what MCP is? It's because if you know how to get your agent to communicate in Model Context Protocol, you can bypass having to write your own custom middleware to interact with all of these endpoints. That's going to save you a ton of time on projects you're doing, a ton of money you would have had to spend if you were, let's say, building a company. It's really useful to understand how to get your agents to interact following MCP. In terms of which LLMs or agents you should use for MCP intensive tasks, we can find the answer to that question by looking at what the scientific literature says. Down here I have, or rather in the middle of the slide here, I have a figure that was sourced from the paper that's referenced down here in the bottom right. And this is coming from a paper called MCC-Bench, where they were assessing tool using agents on tasks. And just to be very clear, the way that this has moved, this here being commercial LLMs like GPT-5 have moved in recent years, is they've really leaned into the use of tools to solve more sophisticated problems. And so the general workflow that MCC-Bench was trying to assess was they stood up a set of 250 or so real-world MCP servers, examples similar to what I showed you here. And then they gave these MCP servers as inputs to LLM agents. So the agents understood what the servers were and could call them to perform certain tasks. And then they had some criteria they used to assess which LLMs were able to perform the tasks most effectively using these servers that were at their disposal. This is important. It's a little nuanced, but it's important because, if you were going to assess these LLM agents' performance, even though they're tool calling through MCP, they still may need to know how to orchestrate the tools to get the answer, right? For example, let's say we wanted to know the age of every baseball player in Red Sox team. Well, what we might need to do is go to Wikipedia, find who all the players are. So that's one tool call via MCP. And then we may need to call some other server that gives us additional information on each of the players within that. So there would be a planning step and 2 tool calls that would be needed in order to answer the question effectively, right? And some of the rules-based judgment that you see down here, which we're going to cover in the next slide, will give you some insights into that. So jumping straight into it, what you can see here on this admittedly very dense table is a couple of axes in which they were assessing different models. As context, I'm showing this to you because if you're going to go implement an AI agent in a production ecosystem, for example, at your job or your startup company, then you're going to have to choose one of these models to use. And so it's useful to know which of these models is better or worse at using MCP, and if they are better or worse, along what axes. So here we have the models for you to look at, and there's a lot of the usual suspects. We have the Llama models from Meta, we have the Gemma and Gemini models from Google, the OpenAI models, and some of the other common methods here. And each of the columns here is giving an axis in which we can perform a comparison of the models that you see in each of the rows. So you can see here we have some rules-based assessment of the models. Specifically, they were looking at how well the schemas could be understood, and these are the MCP schemas as I understood it. So when these LLMs needed to call a tool, were they able to generate a valid tool name? As we're going to see when we do the code implementation of MCP in a few slides, being able to name the tool that you want to use, given what the server returns to you, the MCP server is important, right? You have to know the name of the tool if you want to use it. What you can see here is that there's almost no difference. I mean, some of them notably GPT-5 in their benchmark and Claude 4 Sonnet from Anthropic nailed it 100% of the time in all of the examples. Interestingly, these are sort of the two preferred models for the use in coding tasks. So that's sort of an interesting note here. There's two other axes that they looked at, which was schema compliance and execution success. I think between these, maybe focusing on the execution success here is a little more important. Key thing for you to take away is that if we compare, let's say, the top two with respect to the ability to call valid tool names, Claude 4 Sonnet versus OpenAI's GPT-5, according to this benchmark. OpenAI's a little better, but I mean, not much. This might even be just noise. So this is based on the ability to understand the schema related to model context protocol and execute the tasks effectively. They also used an LLM to judge the outputs of these tool calling agents that we have along the rows. And the specific outputs they looked at were, did they call the right tool, which is different than can they call a tool? Can they remember the name? Did they call the right tool? And were they aware of dependencies? So how you sequence the sets of tools to solve the problem? And how efficient were they? Okay, these are sort of the three main things I want you to pay attention to. If you look across these, first, the tool appropriateness, you do see a really significant difference between GPT-5 here in the benchmarks and the other models here. For example, if we come here to Claude Sonnet 4, we're seeing almost a 0.1 difference in the performance, okay? And I believe that this maxes out at 1, so that's a pretty large or significant difference between what we see down here and what we're seeing up here. If we jump over to the dependency awareness, we can see a similar trend that occurs. Claude 4 Sonnet sits at around 0.55. We've got this sitting at 0.67. In terms of parallelism and efficiency, it's not that much of a difference. So what's the overall story that you should take away from this chart is that if you're going to be building an agent that will be tool calling with MCP, you should probably be using one of the OpenAI family models. That's why, not coincidentally for this class, I suggested in some of the homework assignments that we use the OpenAI models, because practically speaking, if you were going to if you were going to build a production grade system, tool calling is going to be important. If you're going to be doing tool calling, you'll probably be using MCP, and you want to use the model here that can do the tool calling most effectively. Okay, let's do a quick overview of the main components of model context protocol, or the main components rather, that are involved when you're doing model context protocol, and then we'll jump into a code example. So the first thing is you have a client, okay? And this is usually a wrapper around an LLM. So it acts as an intermediary that translates the LLM's intent into the formal request that conforms to the MCP standards. You can also have the LLM attempt to output the standards of communication, the specific format, for example, of the JSON object that the server is expecting. But typically what you do is you handle that as a separate step, and the MCP client takes responsibility for that. The client sends either invocations of tools, queries for resources, or interpolation of prompts to an MCP server. And this MCP server, as we've alluded to, acts as a gateway to the external world. It exposes those sets of tools and resources to the authorized MCP client. What are the tools and resources? Well, the three categories that are oftentimes discussed in the context of MCP are here. So we have model-controlled functions evoked by the model. So we might want to retrieve or search, send a message, update a database record. These are kind of tool calls. We might have manipulations of files, database records, or API responses for application-controlled resource manipulation. And then, of course, we might also have some predefined templates for standard AI interactions. These could be prompt templates like what you did in your first homework, that when the MCP client calls the server, it knows it needs to execute a certain prompt in order to generate an output that's relevant back for the client. Okay, these are sort of the three major components. Now let's start to jump into the nuts and bolts of the actual protocol itself. How is it structured, and how does it get used? Because if you're going to build a protocol, English, for example, is a protocol of communication between English speakers. There's going to be some rules, right? You know, we have nouns in English. We have when we use the word the to denote something, how we denote gender using certain kinds of pronouns, and so on. And a model context protocol also has certain rules that we have to follow in order to be in adherence with the protocol. So the first is when a client wants to request a service from the server, so the client wants to make a request to the server, it sends the request over HTTP, for example, okay? Or it could do it if it's sitting locally as an endpoint within your code base, you could just call it not through HTTP. You pass in as an input a JSON object. And specifically, you have to pass in within this JSON object a field, JSON-RPC 2.0, which is the protocol version that you're going to be following. And it's always 2.0 in MCP, at least as at the time of this recording. You also pass in an ID for your request. And then you pass in a method, which is related to, like, what do you want to do? What's the requested action here? In this case, you want to get the list of tools that the server has access to. And this is standard. So if you want to know what the tools are in any MCP server, you always pass in this JSON input, and you will always get the corresponding output of the list of tools, which is great, right? If you know how to do the tool request on one server, you can do it on all servers. When you're requesting information on tools, there is a parameters file here, which, because you're just requesting information, you typically don't have to list any inputs there. Now, the MCP server is going to issue a response to you from that input, and that comes from them back to you. Some of the elements here will look familiar based on the input. It will respond with the JSON-RPC version, which again is 2.0, matching the request. It will give you the same ID as the request so that you can correlate in case you're sending multiple requests, for example, to the server in parallel. You want a way to keep track of which response corresponds to which request, because different requests could take different amounts of time and so on. And then really the major payload here, the thing you care most about, is the result. So before, in the request, we had asked for a list of tools through this method. And what it provides us in this section is the actual result, right? The set of tools, which is contained within a list of objects that you can see here. Each of the JSON objects within the list correspond to a single tool. Now, in this example, so that I could make it very easy to follow, we only have one tool. That's math.add. One thing to note is that if you want to be adherent with an MCP protocol, this name has to be unique. So within the server, we could only have one math.add method that could be called as a tool. You can't have 2, 3 redundant versions of those. For each of the tools, which has a corresponding name, there's a description of what it does that needs to be human readable, which gets returned. And then, very importantly, an input schema is passed that tells you, how do you interact with this? What do you need to pass into it in order to get a response from it? And in this case, what it returns through the object properties here is that a property A is required, and it's a number. A property B is required, and it's a number. And it notes that if you don't put A or B, I'm going to return an error to you. These are both mandatory for the use of the math.add tools. So to recap, we have asked the server, hey server, what tools do you have available? It responded to us and said, I have one tool. It's called math.add. The next thing we might like to do is use that tool. And this is showing a client request for a service where we're going to call a very specific tool, as denoted by this method, tools.call. Not tools.list like we had before, or tools/list. Now it's tools/call. Once we're doing a tool call, now this parameters, instead of being empty like it was when we were listing the tools, we got to pass in some parameters, namely, which tool do we want to call? And in this case, it's math.add, which was the one tool that was available in the MCP server. You may recall when we were back here, the MCP server told us that there were two inputs, A and B, both of which were numerical and required. And therefore, you can see in the corresponding arguments, we respond with those two entities, A and B. And so naturally, as you'd expect, some of the items here are the same. When it responds, it gives some of the header information like the ID and the JSON-RPC version. But importantly, it gives the result content here, which contains the result of the 2 plus 3, calling the math.add tool, which is 5. Great. So if you understood how MCP works up to this point, which is it sits between a LLM that makes requests following a certain format and some downstream tools like math.add in the context of the simple example, and the code that we're going to cover here, I think will allow you to see just how easy it is to set up an MCP server as well as an MCP client. So let's start with the server side. As we've been doing in previous lectures, I put some of the dependencies here on the first page before we get into the actual code. So in this case, I'm assuming that the server is a Flask application, which is what you're using in the class when you build the assignments. I also have here this global variable called tools. This should look pretty familiar, right? This is actually identical to what we were covering in the example. It's the same object, math.add. It has a description, and then there's an input schema, which says, what are the properties, A and B, what are their types, and whether they're required. So if we wanted to add 3 more tools, we would take this tools object here. We would, at the end of this list here, add a comma, and we'd list additional tools that we were interested in having in our tool set. Okay, but for the sake of this example, it's just going to be math.add. Now, this is a Flask application. And so, as you know, in a Flask application, we have certain routes that we can interact with. In this case, I've got a route/RCP that we may call in order to get a response for the math.add tool that we built. So how does this RCP function actually work in practice? Well, we had mentioned that if you want to use Model Context Protocol, it's going to expect as an input a JSON object. And so we go to the request, which is passed in via HTTP, and we extract the JSON object from that request. So it's assumed it's going to be JSON because of Model Context Protocol being followed in this example. We also get the ID object from the request, okay, because they always contain an ID as we showed up here. We then come and get the method, which back here, you may recall when we made a request, there was a method. okay? And then similarly, we get the parameters, which, as you recall up here, there were some parameters. Okay, so now we've taken the JSON object and we've parsed it. We've pulled out the ID, we've pulled out the method. So what's the action that the client wants us to do, as well as the parameters. And there's three methods that if you want to be adherent with an MCP build, you have to have integrated in your server. The first is the initialize method, which needs to return the protocol version. The second is what we saw in the example, a method that will help us list the tools. Okay, in this case, it's going to construct the JSON object that you saw in the previous slides. Specifically, let's come back up here. Remember tools.list on this slide? Returned an object like this, where we had a tools object, and then for each of these, we had a name, a description, an input schema, and so on. If we come back down here now, you can see it adds a name, a description, an input schema for each of the items that's in tools. That's how we actually get the response in the right format back. We add to this the tools that are generated here, just as you saw before. That gets added to a component of the response called tools. And this result will ultimately get shipped back along with the JSON, RCP, and ID back to the user. Okay, so that's the list method. Let's look at the call method next. So now we might know that there's math.add as one of the tools. We want to now implement or interact with math.add. And if this is what we want to do, we need to get the name of the tool. So if this were a reasonable call, this would be the math.add. And then we want to get the arguments. That was the A and the B that we saw earlier in the lecture, the two things we wanted to add. We're then going to call the tool, which up here would, in this very simple implementation, just looks for each of the tool names. And, you know, there's one tool name, so we've got just math add, does the addition between the two values and returns as a string back to the user. And then stores this in the result, just like we saw in the previous slides. So this is an example of us implementing the server side of Model Context Protocol with a little bit of error handling down here, which is required per the protocol. Of course, in order for us to actually use this, we not only need the server, which will take the request and issue the response, we also need a client that can issue the requests in the right format. And so for the client, with our agent sort of built into it, these are the libraries that we'll be using. So we're obviously going to need our environment, which is going to contain the OpenAI API key. And we're going to need the location for calling the RCP or Model Context Protocol server, right? Typically, when you set up a Flask app, it gets hosted on 8000 or 8080, which is why this is sitting at localhost. Okay, this just tells us if I want to call the RCP function that's here, right? This server, what's the actual URL I'm going to use to call it? So with that, actually the interaction between our client now and the Model Context Protocol server becomes very straightforward. We have up here a method which basically takes care of packaging certain parts of the payload, so which is the method, the parameters, and so on, and make sure that it's in the right structure, the right JSON object structure, so that when we transmit it to the endpoint, everything that's required in order to generate the response is available. So that's all this RCP does here. What we have downstream of this are some kind of examples of how this would be used within an agentic workflow. A user might ask, add 7 and 5. We'd run the initialization. We would try to get the tools by calling tool list. And then we might have a system prompt that says, okay, you're an MCP client. Here's the tools, which comes from whatever the Model Context Protocol server returned for the tool list. And then we tell it we need you to output a JSON-like object, something like this, with the action that you want to do, the name of the tool, and any arguments that would be divulged in this tool set here. If none of these tools are needed, just answer plainly. And then it's very simple from here, right? We're going to evoke the LLM with our system prompt and the user's text, in this case, add 7 and 5. And then we're going to figure out what the action is. And because of it being an MCP set of actions, we will know basically if it starts with a open curly brace that it's responding with a tool call. If it doesn't, we assume it's a standard one. That's what this line does, so we can get the action. If the action ends up being a tool call, fantastic. We're going to call the tool, and we're going to pass in the action name and the arguments. In this case, it would be the 7 and the 5. And if it's not, we're just going to respond without the use of tools. Okay, so this shows how you do the client side of the interaction with the server that we just set up on a Flask app, for example. As you can see, it wasn't that many lines of code. So building Model Context Protocol into your application is not actually terribly challenging. It's also important to note that if you're building APIs, you're not in the business of building agents, but like you serve data or information, or you have a machine learning model that's really good at something. Having an endpoint within your application, let's say it's a Flask application, that allows people to communicate with your API, with your model, with your data ecosystem following MCP could be a great way to sort of future-proof some of your offerings. So I hope that taking you through this full example of how to implement MCP is helpful. We're going to end the lecture by very quickly covering exception handling. Exception handling refers to detecting errors and handling them. Okay. Typically, this involves validating the outputs of tools that you might evoke through MCP, checking API error codes, or using timeouts of some kind. So the workflow here is if a user injects or provides a prompt, and the agent is going to execute the prompt, there's going to be some subset of contexts in which the agent fails. And you may need to trigger an exception handling routine so that the agent can include that exception within its response to the user. At its simplest, that exception handling is, I'm sorry, I couldn't answer your question, please try again. Or perhaps if it's beyond the capability of the agent, informing the user that a human is needed to answer the question. In practice, the way that this exception handling is performed is through reflection, which is what we covered in previous lectures. So you make an initial attempt at the problem, and then you ask another agent to reflect on whether you answered the question correctly or not. Basically, be critical of this agent's output. If it turns out that a separate agent thinks that the response was no good, the reflective process can help analyze the failure and perhaps update the prompt to reattempt the task. As a fail-safe, assuming you try it a few times, you may need to go back to either telling the user you're not able to solve the problem, or by alerting a human to get involved with solving the problem. I don't have a code example for this one because when we covered reflection earlier in the lectures, reflection sort of implicitly covers exception handling within models. I thought it would be useful to end our lecture today, though, talking about exception handling, because when you start using MCP to build more sophisticated agentic implementations, there's going to be instances where certain APIs may be down, they may not react as you expect, and having a part of your workflow in place where you can catch those unexpected behaviors from the tools and the APIs that your system depends on are absolutely necessary if you want your tool to function effectively. So that's it for today. I hope that this was helpful, and I'll see you in the next video.